Okay, let's take a look at question number 2 in the warm-up. So if I've got the same concentration of HCl versus HCN, you know that HCl is a strong acid, so it's going to dissociate into hydrogen ions and chloride ions. So if this is 0.1 molar, this would also be 0.1 molar. So if you're trying to figure out the pH is the negative log of the hydronium ion or hydrogen ion concentration, so your pH would be 1, okay? Over here for this one, HCN is going to dissociate into hydrogen ions and cyanide ions. So if this is 0.1 molar, technically this is a weak acid, agreed? Mm-hmm. Okay, so if this is a weak acid, technically this should have less than 0.1 molar and less than 0.1 molar in real life. But if you're trying to figure out what the pH is, the pH is probably going to be less than 1, okay? And number 3, assume that 25 mils of each solution reacts with 0.1 molar NaOH. How will the volume of the NaOH solution required to neutralize the HCl compared with that required to neutralize the HCN? Well, they say that the volume of NaOH would be the same to neutralize each. In reality, we should do an experiment to see that, okay? To see if the percent ionization of HCN contributes to its pH being slightly different. Actually, wouldn't this be greater than 1? Because it's weak. Yeah. That was a mistake. Okay. So let's take a look at the criteria for titration. A lot of this you've already heard before. Some of it will be reviewed, some of it will not, and I'll point that out as we get there. So you guys know that titrations are specifically referred to as volumetric analysis because you're using volumes of liquids to analyze each other and figure out the unknown concentration typically. And then any reaction that you consider for a titration has to satisfy 3 criteria. Only one reaction should be occurring between the 2 solutions. The reaction should go to completion pretty quickly. And then number 3, there must be a way of signaling the point at which the equivalence point is achieved. Equivalence point or stoichiometric point would be considered the same thing. And an equivalence point in an acid-base titration happens when the total number of moles of hydroniums from the acid equals the total number of moles of hydroxide from the base. Let's see what else we need. To make sure that the reaction between acid and base goes to completion, one of the 2 reacting species has to be strong. And then the correct indicator is one that will change color very close to the pH that is associated with the equivalence point. Let's take a look at the next page. You guys know that a standardized solution is the one that is the solution of known concentration. The solution in the burette is called the titrant. Solution in the flask is called the analyte. The rest of it you know. The rest of it you know. I'm not going to bother highlighting it. Let's see what else. They're kind of being redundant. Here, right here. If the volumes delivered from the burette in the first 2 trials do not agree, within the desired uncertainty, then the titration has to be repeated until they do. Let's take a look at the table at the bottom of the page. Here you'll notice that the table has given you 3 different volumes based upon the trials, 21.3, 21.1, 21.2. Typically, you would want them to be within 0.1 mils of each other. So that means this one would be thrown out. Go to the next page. Let's go to standard solutions. Some of this is going to be new. There are 2 ways to obtain a standard solution. If you've got a soluble compound in a really pure form, then you can have something called a primary standard. There are 2 examples of acidic primary standards. Potassium hydrogen phthalate. This is typically abbreviated as KHP. Okay, this is a monoprotic acid, and then oxalic acid dihydrate would be the other one. That's a diprotic acid. If you're looking at a basic primary standard, you're looking at sodium carbonate without water attached. This will accept 2 protons when it reacts with an acid, and then I believe that is it. We're going to be using, I believe we use KHP in a lab that we have yet to do, okay? And then down here at the bottom, if you're dealing with an NaOH solution, the reason why we like to make NaOH immediately before we use it is because stuff in the air will actually dissolve in the solution. So here it says atmospheric water vapor or carbon dioxide especially will dissolve in it, and it will change its concentration. And then what you have to do is immediately before you do a titration, you have to standardize it, which means you have to figure out what the concentration is immediately before you use it, okay, in order to have the result for your titration actually be accurate. Here it tells you right here that solid NaOH rapidly absorbs water vapor from the air. And if you go on to the next page, NaOH reacts with carbon dioxide to form sodium carbonate in water. So that means that that's really why your concentration is going to change. I think that's all that we need to know there. All right, now for using KHP or oxalic acid. KHP, you may want to earmark this page. KHP reacts with NaOH according to this equation here. You may use that later in a lab. So that's why I'm telling you to earmark the page. Oxalic acid dihydrate reacts with sodium hydroxide in a 2-to-1 ratio. Here is the example. So here and here, just use that as an example for later. And then this tells you that if you're trying to use KHP to standardize NaOH, meaning use KHP to figure out what the unknown concentration is for NaOH, you usually measure out a really precise amount of KHP, and then you put it into a volumetric flask with some water, and then you make a really accurate or precise concentration of it. I think that's about all I need to highlight there. Okay. They also tell you some appropriate indicators on this page in case you need it later. Oops, let's come down. Okay, let's take a look at question number 1 and 2. So with the person sitting next to you, Why don't you fill out 1 and 2? And let's see what you guys can do. Okay, what did you say for number 1? Good job. Why?
Reacts with
It's
air.
exactly
CO2.
It reacts with what?
CO2 in the air.
Yeah.
Part of it. NH2.
Yeah, exactly. Number 2A. Yep. Number B or letter B. Huh?
Titration against an acidic primary.
Here's what I would say. Because that means you're finding out its actual concentration at that moment. And then C. Yeah. And then the last one.
indicator.
Okay. I think you guys know how to do the titration calculations, yes? Okay. All right, so good news. We're going to turn the page, and then we're going to turn this one also. We know how to do that. We know how to calculate volume. How about calculating molar mass? You want to do that one? Okay. Okay, so we've got a certain mass, which we'll use later, of an unknown monoprotic acid. Generally speaking, you're going to abbreviate a monoprotic acid as HA. And then you've got 750 mils of solution. You got a 25 mil sample of it. 12.5 mils of 0.104 molar NaOH is required. Calculate the molar mass of the acid. Okay, so acid HA plus NaOH is producing salt NaA plus water. And then you've got 12.5 mils of this, 0.1104 molarity, and then you took 25 mils of this, don't know what its concentration is. Agreed?
Mm-hmm.
Okay, so let me do this in a different color. All right, so then you're going to take your 0.0125 liters of NaOH times 0.1104 moles per liter of NaOH. This is a 1-to-1 ratio. And then put this over 0.025 liters of the acid. And then this is going to give you 0.0552 molar HA. So that's the concentration of my monoprotic acid. Then take that times the original amount. So you guys know, based upon the molarity triangle, that molarity times liters will give you your moles. So if you take your 0.0552 molarity times 0.75 liters of acid, you're going to get 0.04-ish moles of acid, okay? So if you want your molar mass is grams per mole, right? So that means you need to take your 3.648 grams divided by 0.04 moles, and then that's going to end up giving you somewhere around 88 grams per mole for your molar mass. Okay.
Would they ever ask you to like find the unknown monoprotic acid based on the molar mass, or can we not do that?
Possible. if they